Hello! The power outage made me think about providing backup power for my apartment. On one hand, there are many offers for ready-made solutions available online for various budgets, but they are still far from cheap. There are also many videos of people performing various versions of similar solutions on their own, and in the vast majority of cases, they look, to put it mildly, not very safe, either with a clear violation of operational parameters or presenting the desired as actual. After researching a lot of different information, I settled on this particular option for implementing my initial idea. As with most of my fellow countrymen, the most important parameters for me were the price-quality ratio, safety, duration of operation, and automatic switching. I will explain what is inside, how it works, and why I chose this particular option in this video. So make yourself comfortable. I will explain in as much detail as possible, from theory and honest calculations to practice and testing. This is the video that I was looking for myself and couldn't find, so I decided to create it and perhaps help someone with this seemingly complicated issue. First, it's about batteries. Here, maintenance-free lead batteries are installed, specifically 12-volt calcium-calcium car batteries, each with a capacity of 74 Ah. I chose maintenance-free batteries because their design is such that during charging, the vapors that form inside condense on the battery cover and return back. My collection is in the hallway, so the vapors of sulfuric acid or the explosion of dangerous hydrogen is definitely not something I want in my apartment. You will say that these batteries have two emergency vents on the sides, through which vapors can still escape to the outside. And you will be right. If the recommendations for charging or operating these batteries are not followed, they can indeed emit hydrogen or vapors of sulfuric acid. Therefore, just in case, I connected the tubes to these emergency outlets and led them into the entrance, which is in turn a well-ventilated area, frame. To prevent this entire system of wires from being scattered across the floor or from the weight breaking the shelves in my closet, I searched for a long time for materials to make a frame. I don't have a welding machine and there's nowhere to weld it. Paying for this will not be cheap. I decided to give up on wood because I'm not sure it will hold up well, or it will be a bulky frame. In one of the building hypermarkets, I found an interesting Valravin profile. There are a bunch of different fasteners for it. It looks reliable, but these, as they say, are quite pricey. After researching the network a bit more, I found a rather interesting option, which is where I ultimately settled on the Valravin profile. It is used to make various partitions, false walls, and even to hang suspended toilets. Therefore, for my needs, this is exactly what I need. The profile connects to each other with hexagon fasteners, so no welding or special tools are required. I attached wheels at the bottom so that the whole contraption could be easily moved, as it weighs quite a bit, just over 70 kilos. And now, the most interesting part is the insides of the electrical panel. By the way, I chose the electrical panel for a 3-phase meter. It is large enough to accommodate the inverter and the automation, and it costs significantly less than regular electrical cabinets. Inside the cabinet, I screwed a piece of OSB to which I mounted everything else in random places. The switch and relay fit nicely at the bottom on the DIN rail, so I cut out a section on the side of the electrical panel, a hole for the inverter's output so that it cools properly, and the cables to the battery should be as short as possible. I bought the inverter on AliExpress with a pure sine wave rated at 4000 Chinese watts. I mounted a meter on top to monitor the current consumption and the total consumption over the period of operation. At the bottom stands what is now called the automatic transfer switch. But if I'm not mistaken, it should be correctly referred to as the automatic backup power switch. Whatever it is called, we are interested in how it works. In short, when there is electricity in the city grid, the apartment operates on it. When the power goes out, this unit switches the apartment to backup power. It returns to the city grid when the power is restored. To do this, the switch needs to be placed in the circuit break, after the input automatic switch. Here, 3 wires come out from my backup power switch. I will explain why there are 3 instead of 4 a bit later. One is mounted on the neutral bus, one on the output from one circuit breaker, and one on the consumer, that is, on the wire that was previously in the circuit breaker. So why are there 3 wires instead of 4? Because 2 neutral wires are combined into one. It turns out that the neutral from the city grid and the neutral from the inverter are the same wire. I did this to ground one output of the inverter because it provides 2 phases. By the way, having 2 phases at the output is quite a common occurrence even in factory stations from well-known manufacturers. And it is precisely because the inverter has 2 phases at its output that the automatic transfer switch becomes semi-automatic, because it switches from the inverter to the city grid, but not from the grid to the inverter. Therefore, one phase needs to be grounded. I have seen people connect one phase from the inverter to the ground, but I'm not sure that's a good idea. Write in the comments what you think about this. In my case, everything is much simpler. The apartment is in an old building where grounding is absent, so the choice is obvious. This automatic transfer switch was also purchased on AliExpress because here it costs 2 to 3 times and sometimes even more than that. It has additional terminals for controlling external devices. Essentially, these are standard normally closed and normally open relays. I use one of these relays to turn on the inverter when the power goes out. I unscrewed the cover on the inverter and soldered 2 wires into the break of the power button, then routed them into the contact group of the switch. The switch on the inverter is always on, but the wires are open, and the inverter does not turn on until these wires are closed. They are closed by the relay when the light goes out. The light went out, the relay closed, and the inverter started. However, the inverter needs a few seconds to reach its operating voltage. This is exactly why this relay is needed. It performs several functions. The first is a delayed start. That is, after the voltage from the inverter appears at the relay, it waits a few seconds for the inverter to reach its operating parameters, and then it sends this current to the automatic switch, which in turn connects the apartment to the inverter. If you have been interested in similar automatic switches, you have probably come across videos where they switch with a rather eerie sound, a kind of buzzing crackling. This sound is actually due to the inverter reaching its operating parameters. This sound can be avoided if the inverter is kept constantly on, but it will drain your battery while idling, so it is better to do this through the relay. The second function is protection against overload. We can limit the current that passes through this relay. And when the current exceeds the specified value, the relay will turn off, wait for a few seconds, and then turn back on. The waiting time is also adjustable. This is necessary to avoid triggering the inverter's protection if powerful devices remain plugged in when switching to backup power. Or if the inverter is powerful and draws such a load, it will quickly discharge the lead batteries. In general, rapid discharge of lead batteries is a bad idea. Therefore, for example, we limit the consumption from the inverter to 1000 watts. Dividing 1000 watts by 220 volts gives us 4.5 A. This is the value of the current that we specify in the relay settings. But what should we do about peak loads? For example, you are currently consuming 300 watts, the computer, light, television, router, and so on, and at that moment, the refrigerator starts, which can draw about 1000 watts at peak. In total, it adds up to significantly more than what we set on the relay. But this can also be configured in the settings. You can set the activation time based on the load. For example, 2 seconds, and what do we get? When the consumption exceeds 4.5 A, that is 1 kilowatt for up to 2 seconds, the relay will continue to operate. But if the load exceeds 2 seconds, the relay will turn off. These 2 seconds will be more than enough to handle the peak load and start your refrigerator, or for example a well pump, etc. But if there is a heater, vacuum cleaner, kettle, etc. plugged into the socket, the relay will turn off. The light will go out, and you will understand why this happened. You need to unplug the powerful device. The same relay is installed at the entrance of the city network. It is also configured for a time delay for activation and for the operational parameters of the voltage magnitude. This is necessary to protect your household electrical appliances when switching to the city network. Because when the light appears, the voltage in the network fluctuates for some time and can be both low and high. So when the power comes on, the relay waits for 1 minute and then supplies power to the automatic switch, which instantly switches the power supply of the apartment to the city network. This happens so quickly that all household appliances in the apartment do not even notice this transition. The relay also has parameters for the minimum and maximum voltage levels, and if the voltage in the city network is less than 180 or more than 250, the relay will disconnect the apartment from consumption, or it will not turn on until the voltage fits within the specified parameters of 180 to 50. These parameters can also be adjusted and increased, or reduce it. But what about charging the batteries? It's simple. A socket is connected to the contacts of the automatic switch on the side of the city network, into which a charger is constantly plugged in, and when there is power, the batteries are charged. When there is no power, there is no voltage at the outlet, and charging does not occur. The only thing is that the charger must be intelligent. There are many decent options on that express network now, not for all the money in the world. When I had 2 lead-acid batteries, I used a 10-amp charger. When I bought 2 more batteries, I got a more powerful charger because the previous one charged very slowly. There wasn't enough time between disconnections to replenish the charge. A few words about charging. In order for a lead-acid battery to last a long time and not lose its capacity over the year, it needs to be maintained within certain parameters for both charging and discharging. Charging should be done with a current that does not exceed 1/10 of its capacity. In my case, the total capacity of the assembly is 296 Ah. That is, the maximum charging current should be 29.6 A. Right now, I am charging at a rate of 20 A. So far, this is enough to replenish the consumed reserve. It is also undesirable to discharge lead-acid batteries more than half of their capacity. With deep discharge, the plates become coated with insoluble lead sulfate, which reduces the effective working area, leading to a decrease in the capacity of the lead-acid battery. Therefore, it is better to discharge 2 batteries to 50% than to constantly discharge 1 to 0. Now, here are the calculations and live figures after using this station. There are currently a lot of videos where they take the capacity of a battery, multiply it by the voltage, and claim that this is your reserve. But there is always a but. The laws of physics have not been cancelled. The first factor that reduces this value is the efficiency coefficient of the inverter. The second factor is the parameters of the upper and lower voltage limits of the battery, and there is also a small percentage for losses in the wires. For example, my assembly is 12 volts and 296 amp hours. By multiplying them, I get 3.5 kWh. Well, wow. But now we need to consider the efficiency of the inverter. In my inverter, it is 0.9. We multiply 3.5 by 0.9 and get 3.15 kWh. We will deduct 5% for losses in the wiring and obtain 3 kW net. However, such figures can only be achieved by discharging the battery to 0. That is down to 10.5 volts, which is generally bad for lead batteries. It is advisable not to discharge them more than 50%. Therefore, for the long-term operation of the lead batteries, we should use not 3 but 1.5 kWh. This will be the actual amount of energy in our system. We will use this as a starting point. I will discuss consumption using examples from my household appliances. The refrigerator consumes 80-100 watts. The starting current is about 1 kB, but it lasts only half a second, so it can be disregarded. We take a maximum of 100 watts per hour. A personal computer in normal mode, such as browsing the internet, working with documents, and so on, consumes about 150 watts. If you load the personal computer to the maximum, for example, rendering an image, you can indeed use all 500, but I try to schedule such tasks for when there is city electricity supply, lighting. If it is turned on throughout the apartment, it will be 190 watts. The television, to watch a movie or cartoons for the kids, consumes 100 watts per hour. Also, often when the power goes out, the water supply goes out as well. That is why I installed a barrel for backup water supply and an automatic pumping station that consumes 400 watts per hour. But during the 4-hour power outage, it is used for a maximum of 10 minutes in total. This results in 2.5 minutes of operation per hour, and this in turn is 17 watts per hour. Well, let's round up to 20 watts per hour. I hope the math is clear here. If you need clarification, please write in the comments. I will write in more detail how I calculated this. Well, 2 routers for the internet constantly consume about 20 watts per hour. So, what does that add up to? Refrigerator 100, personal computer 150, lighting 190, television 100, pumping station 20, routers 20, totaling 580 watts per hour. In this mode, we will have 1.5 kWh divided by 580 W, which gives us just over 2.5 hours. But I almost never use appliances from the backup power supply, and the refrigerator does not always work. Therefore, if we translate this to a more realistic scenario, we have a refrigerator consuming 50 watts. Let's assume it operates 50% of the time, and a pump consuming 20 watts per hour. Routers consume 20 watts, and without the television and lighting in 2 rooms, which is 60 watts. In total, we have 300 watt-hours of consumption, and our 1.5 kWh is enough for 5 hours already. If we reduce consumption to the minimum comfortable level, that is, turn off the PC, leave the light on only in 1 room, keep the refrigerator running, and also leave the pump and routers on, we will get about 120 watts per hour, and 1.5 kWh is enough for 12.5 hours. And this already takes into account the efficiency of the system and the condition of discharging the batteries to 50%. In unpredictable situations, it is certainly possible to discharge the batteries to 0, effectively doubling the autonomy. But this will not reflect well on the number of cycles of lead batteries, so it is important to try to avoid doing this. Conclusions. Charging stations based on lead-acid batteries have a right to exist under certain conditions. The drawbacks of these stations are their size, weight, and limitations in charging and discharging. However, with sufficient capacity, these drawbacks can be somewhat mitigated. For $677, you can get a fully automatic station with a genuine capacity of 1.5 kilowatt, with the possibility of taking 3 kilowatt from it. Although it is not advisable to do so, in critical situations it is at least possible. In this collection, the charger has a reserve. It is also possible to add another 1 to 2 batteries without any issues and switch to a charging current mode of 35A instead of the current 20A. In fact, I plan to do this if the situation with electricity worsens in winter. As you can see, the most expensive component of this assembly is in fact the batteries themselves. But if you have the opportunity to install the system in a non-residential well-ventilated space, you can use regular serviceable lead-acid batteries, which are almost half the price. Of course, lithium batteries have a greater number of charge-discharge cycles. But these are definitely not the batteries I would want to store at home in a living space, especially not in such a volume. Thank you very much for your attention. Please write your thoughts in the comments and feel free to ask questions if you are interested in something, or if I may have missed something in this review. Thank you for your attention. All the best.